Hey guys, my name is IBM and I'm still taking you through Waves. Waves is actually a very long unit, it's a very long topic, but it contributes a lot to AS physics. That is both the solved, I mean, that is both the multiple choice questions and in the paper too. So you expect a lot of, or about 10 or 9 multiple choice questions in paper 1. And you expect always at least 1 or 2 questions in paper 2 under waves and superposition. So it's supposed to be a longer unit. So I would like to take you to lesson 13, where in lesson 13 we shall basically concentrate on interference of light waves and maybe introduce or we shall even introduce Young's double slit experiment. So let's go to lesson 13 of waves and superposition. So this is basically superposition, and we have already seen stationary waves and standing waves under superposition. We have already seen a diffraction of waves, and currently we are dealing with interference. And in this lesson 13, we are going to be concentrating on interference of light waves, where we shall get an opportunity to introduce Young's double slit experiment, or the method of division of wavefronts in lesson 13. So let us go to interference of light waves. In lesson 12, I think we talked about the principle of superposition, and we were talking about constructive and destructive interference. So, and we introduced the concept of interference fringes, and we introduced the concept of interference patterns, where we said a maximum is formed when waves interfere constructively, and a minimum is formed where waves interfere destructively. So I want you to recall that the superposition of two mechanical waves can be destructive or constructive, as we have already mentioned. And we said in constructive interference, the amplitude of the resultant wave at a given position or time is always greater than the amplitude of either of the individual waves. Whereas for destructive interference, we have already said that the amplitude is going to be less than that of either individual waves. So light waves, just like any other wave, also show interference. We said interference is a phenomenon which can be shown by or demonstrated by all waves. All waves undergo interference irrespective of their type or irrespective of the nature of the waves. So fundamentally, all interference associated with the light waves arise when the electromagnetic fields that constitute the individual waves combine. So when two light waves meet at a point, we expect that the electromagnetic fields, that is the electric and the magnetic fields that make up light, are supposed to combine. And when they combine, if they combine constructively, we expect a high intensity of the electromagnetic wave. If they interfere or they combine destructively, we expect a lower intensity of electromagnetic waves. So let's think of two bulbs placed side by side. Does it mean that two bulbs placed side by side will produce interference patterns? Because these are now going to be two sources of light. Will they produce interference patterns? Probably not. So if we have two light bulbs placed side by side, no interference effects are observed, because the light waves from one bulb are emitted independently of those from the other bulb, even if the two bulbs or the two lamps are joined to the same source. So we have bulb A and bulb B. Even if these two are joined to the same source of power supply, maybe two bulbs A and B will not show or will not produce interference patterns that we have been describing earlier on. That is regions of maximum and regions of minimum intensity. So two light bulbs placed side by side will produce no interference effect which is observable to us, because the light waves from one bulb are emitted independently of those from the other bulb, even if the bulbs are joined to the same source of light. That is the nature of light from bulbs. So the emission from the two light bulbs do not maintain a constant phase relationship with each other over time. Now, the reason as to why we don't see interference patterns, that is, we don't see regions of dark and bright, or maximum and minimum interference patterns, or constructive and destructive interference patterns with the light coming from two bulbs, is simply because the bulbs or light bulbs do not maintain a constant phase relationship between them. So the phase relationship between two independent light bulbs will always change abruptly, irrespective of the other bulb. So light waves from an ordinary source, such as a light bulb, undergo random phase changes in time intervals which are less than nanoseconds. So the light bulb or the light from a light bulb will undergo a random phase change in a time which is extremely small, which is about a nanosecond. And of course, our eyes cannot rapidly follow these rapid changes or these changes which occur in a very small period of time. A nanosecond is 10 to the power of minus 9 of a second. Our eyes cannot respond to such rapid changes. So our eyes cannot detect when the phase was constant and when the phase started changing, because the phase changes randomly in a very short period of time. So light waves from an ordinary source of light, such as a light bulb, undergo random phase changes in time intervals less than a nanosecond. Therefore, conditions for constructive interference or destructive interference, or even some intermediate state, are maintained only for a very short period of time, about 10 to the power of minus 9 seconds. Because the human eye, cannot follow such rapid changes, then the human eye cannot see interference patterns from light sources, especially if the light is coming from two bulbs. So because the human eye cannot follow such rapid changes, no interference patterns are observed. Such light sources are said to be incoherent. They do not maintain a constant phase relationship throughout. Light from two different sources, or light from a light bulb or from a bulb, undergoes random phase change. So light from two sources is not actually going to be coherent. In other words, there is no constant phase relationship between light from the two sources. So similarly, we talked about sound waves earlier on. Similarly, sound waves from two loudspeakers, each connected to a separate signal generator or separate signal generators, they will not produce observable interference patterns as the sources are not coherent. So I'm now bringing in the term coherence. So the difference between these two scenarios is that for sound waves, if you connect the loudspeakers to two independent or to two different signal generators, it means the two loudspeakers are not going to be obtaining waves from the same source, so they will not be coherent. But of course, we can make the loudspeakers to produce coherent waves by connecting them to the same signal generator as we saw in lesson 12. Unfortunately for light, even if you connect the light bulbs to the same power supply, these two bulbs produce light independent of the other. Because remember, for a bulb to light, the filament must heat up. So these two bulbs are going to produce light independent of the other. And for that reason, even if two light bulbs are connected to the same source of energy, they will never produce light waves which are coherent. But for sound waves, if you connect two loudspeakers to the same source, the loudspeakers would produce coherent waves, as we are going to see. So thus, to produce observable interference in light. So if we want to produce observable interference waves for light or in light waves from two sources, the following conditions must be satisfied. The first one and the most important one is that the two waves or the two wave sources must be coherent. We do not see interference patterns at night when you when the two headlamps of a car are flashed on the wall. You don't see alternating regions of bright and dark or high intensity and low intensity. You just see light on the wall. We don't see those patterns because two bulbs of light do not maintain the same phase difference. They don't have the same phase relationship throughout. The phase randomly changes for each of the bulbs. And the change occurs in about 10 to the power of minus 9 seconds or a nanosecond. And I said the human eye cannot follow such rapid changes. Perhaps the phase could be constant or could be the same for 10 to the power of minus 9 seconds and then it immediately changes. So we cannot see the patterns because the human eye cannot follow such rapid changes. However, if we want light waves to form or to produce interference patterns, that is regions of maximum, minimum, alternating regions of high intensity, low intensity, high intensity and zero intensity, then the two wave sources must be coherent. What does this mean? They must maintain a constant phase relationship. They must maintain a constant phase relationship between them. So two wave sources must be coherent. So coherence means maintaining a constant phase relationship between two waves or between two wave sources. Number two, if we want to have clearly observable regions of maximum and minimum, in this case minimum would be zero, the two waves must have the same amplitude so that when there is uh, when there is constructive interference, we have maximum amplitude, which is twice. And when there is destructive interference, we expect to have zero amplitude, which will be total darkness or completely no brightness, for us to be able to easily see the difference between a bright spot and a dark spot. So the two wave sources must have the same amplitude, or the two waves must have the same amplitude, and by the way, they should have the same single frequency, or they should have a single frequency. Because we are going to see if it is white light, then we may not see alternating regions of bright and dark for white light. So they should have a single frequency. Remember, light of a single frequency or a single wavelength is said to be monochromatic. So if we want to observe interference patterns, there are two conditions to be satisfied. The waves should be coming from two coherent sources. Coherent sources, they are perfectly identical. They have the same frequency, same amplitude, and they maintain a constant phase relationship between them. That is what we mean by coherence. So in the sound experiment that we have already discussed above, in the sound experiment, the waves from the two loudspeakers have the same frequency and a constant phase relationship because the loudspeakers were connected to the same oscillator and the amplifier, so they were coherent. However, I have mentioned we could not connect two bulbs to the same power supply and think they will produce coherent light. So, if the waves emitted from the loudspeakers are in phase, when the experiment begins, they stay in phase for the whole experiment. So they maintain a constant phase difference for the rest of the experiment. If the waves from the source were coherent, it means the source will continue to produce a uh, uh, coherent waves or waves which are maintaining the same relationship throughout. But if it was light, at one instant, the two sources produce coherent waves for only 10 to the power of minus 9 seconds, and then another instant, the phase difference randomly changes for one in comparison to the other. So if the waves emitted from the loudspeakers are in phase when the experiment begins, they stay in phase for the whole experiment simply because these ones were connected to the same oscillator and amplifier. Therefore, their source is the same, and this is possible for sound waves and other waves, but not for light waves. So let's first understand the meaning of the word coherence in more details. So our wave sources are said to be coherent if they maintain a constant phase relationship between them. So wave sources which maintain a constant phase relationship, wave sources which maintain a constant phase relationship between them are described as being coherent. They maintain a constant phase difference between them. So if, for example, the sources of waves, we have two sources of waves, A and B, and they produce their waves, and the waves produced will always maintain a constant phase difference between them. You notice that here, these two waves were in antiphase, and all the waves produced are in antiphase throughout. So here we say the waves are coherent. But if you think about waves from two different light sources, for example, you have a light source A and light source B. If these are two light sources, then these two waves, which the waves produced by these two sources are going to be coherent. For a few instants, for example, here you notice that a crest is aligned with a crest, a trough is aligned with a trough, a crest is aligned with a crest. Abruptly, there is an abrupt change in the phase here for two light sources. Here, so it means before we reach this abrupt change in phase, this could have lasted for 10 to the power of minus 9 seconds, maintaining a phase difference for only 10 to the power of minus 9 seconds, and all of a sudden, the phase changes for one of the phase of one of the source changes rapidly, changes randomly. So it means our human eyes, our eyes may not have detected even the point when the phase was maintained. So this is what we call incoherent. So coherent sources are those ones which maintain a constant phase difference. So when we talk about coherence, as far as waves are concerned, we refer to maintaining a constant phase relationship between waves, or maintaining a constant phase relationship between wave sources. That's what we mean by coherent. Maintaining a constant phase difference or maintaining a constant phase relationship between two wave sources. That's what we are meaning, that's what we are calling coherence. So two sources of light emitting waves with random phase difference are called incoherent. Random phase difference. The phase difference changes randomly. These ones are called incoherent. If the two sources of light were emitting waves which have a constant phase difference or a constant phase relationship between them, then we would say the waves were coherent. So I say that light is emitted from sources as a series of pulses or packets of energy. We shall talk about these packets of energy in a unit called quantum mechanics or quantum physics later on in paper 4. Now what happens is that these pulses last for a very short period of time, which time is about 10 to the power of minus 9 seconds or a nanosecond. And between each pulse, there could be an abrupt change in the phase of the wave. There could be a random change in the phase of the wave. So it means if I have two separate sources, I'm saying two separate sources, even if they are joined to the same power supply. Waves from two separate sources may be in phase at one instant, but out of phase in the next nanosecond. And I have said the human eye cannot cope with such rapid changes, so the pattern is not going to be observable. That pattern of maximum intensity, minimum intensity, maximum, and so on and so forth will not be observed. Thus, we definitely say that two separate light sources, even of the same frequency, will produce incoherent waves. Two separate light sources, even if they have the same frequency, they will always produce incoherent waves. Now the question is, how do we produce interference patterns using light waves? It is very possible, but we can't have two different sources of light. We can't have two bulbs to produce interference patterns, because interference is also only going to occur if they have the same frequency, same amplitude, but that's not enough. The two wave sources must be coherent. In other words, they should maintain a constant phase difference between them. Now, this could easily be solved by what Young did, which we shall call the method of division of wavefronts. So how do I produce coherent sources of light if two bulbs, even if connected to the same power supply, cannot produce coherent sources of light for me to be able to generate interference patterns? So what do we do? Um, Young solved this, I think that was around 1801. Thomas Young was able to solve this problem using the method that we are going to discuss here, which is called the method of division of wavefronts. So a common method for producing coherent light sources is to use a single monochromatic source of light. In other words, we are now going to use one bulb instead of two connected to the same source. We are going to have one bulb. So we shall use a single monochromatic source to illuminate a barrier which has two small slits. And this is what Thomas Young called the method of division of wavefronts. So in this method, the wavefront, which is a locus of points of the same phase in a wave, is divided into two parts. So we are having, remember, two slits, we are having two gaps, and we are having wavefronts incident on two gaps. So these wavefronts are going to be divided by these two gaps. Of course, here both interference and diffraction are going to play a role for us to be able to generate what we shall call interference patterns. So the light emerging from the two slits is coherent. Why? Because a single source was used, which produces the original light beam, and the two slits just serve to separate the original beam into two parts. It is the same source. We have a primary source of light here, which is producing these waves. But here we have a barrier, we have barriers here, we have two slits. So as this light passes through these slits, we say that these wavefronts are being broken down, are being divided into two. So this is called the method of division of wavefronts. So we have, this is going to be like a source of light. This is also going to be like a source of light, but these are going to be secondary sources of light. So the single source produces the original light beam, and the two slits serve as only to separate the original beam into two parts. So the two slits are going to act as secondary sources of light, where they are not producing their own light. They're just breaking the one which is incident onto them into two parts. This is what we are calling the method of division of wavefronts according to Thomas Young. So if there is a change in the phase of the light produced by this bulb, it changes for both of the slits, because the slits themselves are not producing their own light. They are actually just breaking down what has been already produced by the bulb. So any random change in the light emitted by the source occurs in both beams at the same time, and as a result, interference effects can be observed when the light from the two slits arrive at a viewing screen. So this is what I've been talking about here. So instead of us having two bulbs to produce light, now I have one bulb, one source of light, which is producing monochromatic light. The light is being split by the two slits. So this is a slit and this is a slit. So these slits are not producing their own light. So it means the light is not depending on the slits, because the slits are not producing the light. The light was produced by this bulb here, but this light is just being broken down into two parts. And if if the phase changes for this bulb, it means the phase has changed here, so it automatically changes for both at the same time. But remember, diffraction plays its role, as we have already mentioned. So if the light waves travel only in its original direction after passing through the slits as shown in the figure A, the waves would not overlap and there would be no interference pattern to be seen. However, of course, we know that instead, the light undergoes diffraction. We say diffraction is the spreading of waves into regions of geometrical shadow. So the light does not continue in a straight line, but instead it spreads into regions of geometrical shadow. So for us to be able to see interference patterns, both diffraction, which is playing a role of making the waves to spread into regions of geometrical shadow, and then interference, which is making or which is responsible for the waves from the two slits overlapping to result into either regions of constructive interference or destructive interference. Both of these are playing a role here. So diffraction makes the waves to spread out from the slits into regions of geometrical shadow. That is the role played by diffraction in the formation of the interference patterns we are going to see. Diffraction makes the waves to spread out from slits into regions of geometrical shadow, and the diffracted waves overlap. Now this is the role played by interference. So interference plays the role of overlapping. The diffracted waves overlap to form what we shall call the interference patterns. So in this animation here, we see that the wave fronts arrive at the slits and they are broken down into two parts. These ones, which are the part which arrives at the upper slit, leaves as a diffracted pattern, and the part which arrives at the bottom slit also leaves as a diffraction pattern. These waves are spreading into regions of geometrical shadow. They're undergoing diffraction, and when the diffracted wavefronts or the diffracted crests and troughs overlap, they form what we call interference patterns. Now, I want you to notice that we have a primary source here. These ones are going to be secondary sources now, S1 and S2, but note that S1 and S2 are not producing their own waves. So it means the waves here and here will always maintain the same constant phase difference or phase relationship between them because they are only depending on the primary source. When the primary source changes, it changes immediately and automatically for both. So S1 and S2 are going to be considered coherent sources, which is different from having a lamp here and another lamp here as this being S1 and this S2. Two lamps, even if you join them to the same power supply, they will always produce independent sources. They will be independent sources of light. The phase of each of the sources changes rapidly without informing the other, or it changes rapidly independent of the other. So that is what we call the double slit. So interference in light waves from two sources was first demonstrated by a scientist called Thomas Young in 1801. And like we have seen, the plane light waves arrive at a barrier that contains two parallel slits, S1 and S2, as we have already seen in the animation. What happens is that the two slits serve as a pair of coherent light sources. So these will be secondary sources, not the primary one, because the primary is the bulb that we had initially. So they serve as a pair of coherent light sources because waves emerging from them originate from the same wavefront, and therefore they will maintain a constant phase relationship between them. And the light from S1 and S2 produces on a viewing screen a visible pattern of bright and dark parallel bands that we shall call fringes. So because the light coming from the two slits is coherent, in other words, maintains a constant phase difference, then on the screen, if the light falls on the screen, we will see alternating regions of dark and the bright parallel bands, which we shall call fringes. We shall see visible patterns of bright and dark, and we shall call them fringes. Of course, we know that when the light from S1 and S2 both arrive at a point on the screen such that there is constructive interference, that is reinforcement, we expect a bright fringe to be formed. So if light arrives on the screen and there is constructive interference, we expect a bright fringe, a maximum or maxima to be formed. And on the other hand, when light from the two slits combines destructively, if it combines destructively at any location on the screen, then we expect a dark fringe to be formed at that point. So we shall have alternating regions of dark and bright, and these ones are called interference patterns. A bright fringe, a dark fringe, a maximum, a minimum. These are called interference patterns. So let us focus on this figure here. So this figure represents a schematic diagram of Young's double slit experiment, where we have of course a primary source this side, and then we have secondary sources S1 and S2, which are just slits. So slits S1 and slits S2 could also behave as coherent sources of light waves that produce the interference pattern on the viewing screen as shown here. So these ones are coherent because they are just breaking down, or they are just dividing the wavefront which is coming from the primary source. So if the waves interfere on the screen so that there is constructive interference, we expect a maximum. And if the waves interfere on the screen so that there is destructive interference, we expect a minimum. And you notice that for a maximum, I have joined only points where the crests are meeting. And for the minimum, I'm considering the center between, of course, if this is a crest and this is a crest, we expect that in between the two crests, there must be a trough. So for minimum, I'm joining the points where uh, the crest is meeting with the trough. So that is always a minimum. So when there is constructive interference, we expect a bright spot. That's why it would appear on a screen bright. And when there is destructive interference, we expect a minimum. So on the screen, it will appear to be dark. So we would see alternating regions of bright and dark, bright and dark, bright and dark. That is what we call interference. That's what we call interference of light waves. So figure B shows an enlargement of the center of a fringe pattern formed on the viewing screen. So this is an enlargement. Although it is appearing white, it is not supposed to be white, but it is easier for me to demonstrate it with white. White corresponds to bright, and then this is dark. So it is these are alternative regions of bright and dark. And you also notice that the spacing between them is going to be the same. Spacing between the bright and the dark, spacing between two successive bright fringes is the same, and the spacing between two successive dark fringes is also going to be the same, and we shall later on call this one X, which we shall call the fringe separation later on. So the interference pattern shows bright, which is maxima, and dark, which is minima regions that appear similar to antinodes and nodes. Remember, the antinodes was a point where there was maximum amplitude, which was as a result of constructive interference, and the nodes were points where particles were permanently at rest, which corresponded to destructive interference. So the bright maximum or the bright regions correspond to the antinodes in a stationary wave, and the darker regions correspond to the nodes in a stationary wave. So to fully understand what really happens, we have already explored this in lesson 12, but we can still do it here. So the figure below shows some of the ways in which two waves can combine at the screen to form the observed pattern that we have already seen earlier on. So let's say in A, we have two slits, S1 and S2. These are sources of light, but these ones are coherent because they are receiving light from the same major source. So if waves travel the same distance to reach point P, it means the path difference is 0. The phase difference is also 0. And if the path difference is 0 and the phase difference is 0, we say the constructive interference occurs, which means we expect a maximum at point P, which is a bright fringe. Alternatively, you can count the number of waves. So this is, if I draw a line through this, so 1, 2, 3, 4, 5 and a half. If I draw a line through this, 1, 2, 3, 4, 5 and a half. So here it means the phase difference is 0. They are traveling the same distance from their sources to the center. And remember, whenever the path difference is 0, or whenever the phase difference is 0, it means the waves travel the same distance to reach the screen. And if they live in phase and also arrive in phase, it means constructive interference has occurred at that point, so we expect a bright spot or a maximum. Then if at Q, the waves from S1 are traveling a longer distance from the waves at from S2. But if you count the cycles 1, 2, 3, 4, 5, 6 and a half, 1, 2, 3, 4, 5 and a half. So you have 6 and a half, and then you have 5 and a half. So the difference between 6 and a half and 5 and a half is one wavelength. So here the path difference is still one wavelength, and when the path difference is one wavelength, it means the phase difference is 360 degrees, and that is still constructive interference. So at Q, because at Q there is still constructive interference, a crest, you even see from the diagram, a crest is arriving at the same time with a trough. With the crest of the other wave. So again, we have constructive interference, which would give us a bright fringe. Then in part C, I can count the waves. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. So I have 6 wavelength for the first one, then minus 1, 2, 3, 4, 5 and a half. So minus 5 and a half, which gives us a half wavelength. A half wavelength corresponds to a phase difference of 180 degrees. And remember, 180 degrees, we called it phase. That is, a crest is meeting at the same time with a trough. Even the diagram shows that a crest is arriving at the same point with a trough. A crest is being aligned with a trough. If a crest is aligned with a trough, destructive interference occurs, which will result into a dark fringe. So we would have alternating regions of bright and dark, bright and dark, bright and dark fringes all through. That is destructive. That is how interference patterns are formed with light. So we have seen that in A, are the two waves which leave the two slits in phase strike the screen at the central point directly opposite the middle point of the slits. And because both waves travel the same distance, they arrive at P in phase. In other words, the phase and the phase difference between the two waves of light is 0. So the phase difference is 0. As a result, if the phase difference is 0, we have constructive interference, as mentioned earlier on, occurs at P, and a bright fringe is observed at P. This interference pattern, which is formed at the center, is called the zeroth order. That is, it corresponds to n equals to 0, or it is called the central maximum, or the central order. So the bright fringe, which is formed just at the center between the two slits, or between the two sources, is normally called the central bright fringe, or the zero order maximum, or the zeroth order maximum. It is the zeroth order maximum. Then we have also seen what happens in B. So in B, we have seen that in B, the two waves also start in phase, but in this case, the upper wave has to travel one wavelength further than the lower wave to reach at point P. So we saw that the upper one traveled the distance, I think traveled 6 wavelength, and the other one traveled 5 wavelength, and the difference was 1 wavelength. So the path difference is 1 wavelength. So we say that the upper wave falls behind the lower one by exactly 1 wavelength. So the path difference is a full wavelength, or a whole wavelength. A full wavelength corresponds to a phase difference of 360 degrees. Still, when the path difference is a full wavelength, or the phase difference is 360 degrees, they still arrive in phase at Q. So they still arrive in phase at Q. They interfere constructively, and so we expect a bright spot at Q. This one is going to be called the first order If the path difference is one wavelength, so we come up with what we call the first order bright fringe. So this one is labeled n equals to 1, the first order bright fringe. The central order is labeled n equals to 0, the 0th order bright fringe. We don't have a 0 order dark fringe, as we shall see. So it is the first order bright fringe or the first order maximum to that effect. Then let's talk about C. For C, we have also seen that in C, between points R and Q, the upper wave has fallen half a wavelength behind the lower wave. So here we saw the other one was, I think it was 6.5. 1, 2, 3, 4, 5. No, the other one was 6, and this one was 5.5 wavelength. So the difference or the path difference is 6 wavelength minus half 5.5 wavelength, which was a half a wavelength. So the upper wave has fallen half a wavelength behind the lower wave. That means the upper wave has actually traveled a longer distance than the lower wave. So this therefore means that the phase or the path difference between the rays of light is going to be lambda over 2. The two rays must be in antiphase. We call this antiphase, or 180 degrees out of phase. So in this case, therefore, or this means that if a trough of a lower wave overlaps with the crest of the upper wave, and the diagram also shows that. If you look at this point here, it's like a crest is overlapping with a trough as the waves reach point R. So in that case, we say destructive interference has occurred. So destructive interference has occurred at point R. And whenever we have a destructive interference for light waves, this results into what we call a dark fringe. Zero intensity if the waves are perfectly identical. So for this reason, a dark fringe that is a first order minimum is observed at R. So the orders are going to be above and below, but we don't have a zero order minimum. We have first order minimum, second order minimum, and so on and so forth. But we can have a zero order maximum. That is when the path difference is 0. Okay, so that is what we call Young's double slit experiment. So in summary, when do we have a bright fringe, or when do we have a maximum, or when do we have antinodes? So bright fringes are seen where constructive interference occurs. And remember, for constructive interference, we say the path difference is a whole number times n, times wavelength, where whole numbers start from 0, 1, 2, 3. Or we have said the phase difference is a whole number times 360 degrees, or a whole number times 2 pi in radians, where n equals 0, 1, 2, 3, and so on and so forth. Then for a darker fringe to be formed, or a minimum, or a node, we know that these ones are seen when destructive interference occurs. And when does destructive interference occur? We saw that the path difference is either n plus a half of wavelength, or 2n plus 1 of wavelength, where n is equal to 0, 1, 2, 3, and so on and so forth. So this is the path difference. So the equivalent phase difference, the phase difference we just remove wavelength and put there the equivalent. Wavelength is distance. This is a complete cycle, and the complete cycle is 360 degrees. And this is half a cycle. So I could also have written this as 2n plus 1 into where there is 360, I would put there lambda over 2 is half a cycle. I would put here 180 in degrees, or I would write n plus a half times where there is 2 pi. Remember, it is a half a cycle, so that would be pi in radians. So that would be the phase difference. So if the waves discussed above left the two slits in antiphase, that means if this is a slit 1 and slit 2, and the waves leave the two slits with a phase difference of 180 degrees, then they would arrive where they arrived in phase, they are going to arrive in antiphase. And where they arrived in antiphase, they will arrive in phase. So that means in the previous experiment, the waves were leaving the sources with a phase difference of 0. And we had points of maximum and minimum, maximum, minimum. Now, if the two waves leave the sources with a phase difference of 180, now when they arrive on the screen, where we had a maximum, it now becomes a minimum. So in other words, the maxima and minima swap positions. So if the waves discussed above left the two slits in antiphase, if they leave the sources or the slits in antiphase, then the bright and the darker fringes would swap positions. The illustration we did was considering waves living in phase. But if they had left in antiphase, then we would expect them to swap. We would expect where a bright spot was formed when the phase difference was initially 0 for the two sources, we shall have a darker spot when the phase difference for the two sources is initially 180 degrees. So in other words, the bright and darker fringes would swap positions if the waves left the sources in antiphase. A few things to note before we conclude this lesson. Note, the double slit interference pattern shows bright and darker regions that appear similar to antinodes and nodes of a standing wave pattern on the string that we discussed earlier on. We saw the wave patterns on the string. While both patterns depend on the principle of superposition, there are two major differences we need to talk about. There's a difference between the bright and darker fringes for light, the antinodes and the nodes for standing waves. What is the difference between these two? Waves on a string propagate in only one dimension, while the light waves or the light wave interference patterns exist in 3 dimensions. That's number one. For a string, the waves are in only one dimension. But for light, the waves propagate in 3 dimensions. That's a big difference. And number two, the standing wave pattern represents no net flow of energy for a stationary wave, while there is net energy flow from the slits to the screen for the double slit interference pattern. So for a stationary wave, there is no net flow of energy. But for the double slit interference patterns, when the patterns are formed, there is energy flow from the slits to the screen where the patterns are formed. Yet for stationary waves, there is no net flow of energy. These two factors or these 2 points are very, very, very important. Let us understand more about Young's double slit and the double slit equation in lesson 14. I think it's going to be lesson 14. See you in lesson 14 when we are talking about the double slit equation. Until next time, bye bye.